This is content of part 5b. If you're interested only in specific part of this video, just jump to its start time. Next, I would like to talk about the dependency between anisotropy field and coefficient of spin-orbit interaction. Both parameters are evaluated from the linear feed. Coefficient of spin-orbit interaction is a slope here, and the anisotropy field is the offset of the linear feed, so here or here. I would like to note that coefficient of spin-orbit interactions depends only on the strength of spin-orbit interaction. In fact, it is a numerical indicator of the strength of spin-orbit interaction. In contrast, anisotropy field depends on both spin-orbit interaction and intrinsic magnetic field, which include demagnetization field. The reason why there is such a dependency can be understood as follows. Coefficient of spin-orbit interaction describes the dependency of the spin-orbit interaction on the total magnetic field. It doesn't matter what kind of magnetic field it is. Coefficient of spin-orbit interaction, just proportionality coefficient of this. Coefficient of spin-orbit interaction describes how fast the anisotropy field increases with increase of magnetic field. Or in other words, how fast the spin-orbit interaction becomes stronger when the magnetic field increases. The slope of the increase is independent of the kind of magnetic field which causes it. In contrast, the anisotropy field characterizes how the intrinsic magnetic field, which exists inside the nanomagnet even in the absence of external magnetic field, influences the magnetic properties of nanomagnet. The spin-orbit interaction enhances the influence of the intrinsic field. Therefore, the value of anisotropy field reflects both the intrinsic magnetic field and the strength of the spin-orbit interaction. In a case, if there were no intrinsic field, these two lines would cross each other at zero anisotropy field. If you extend this line till anisotropy field equal to 0, you will get the intrinsic magnetic field. Here, for example, here somewhere here, for example. The clear relation or dependency between coefficient of spin-orbit interaction and anisotropy field. For example, let's take a look at the measurement of this wafer. Just go here, all measurement data. It's this sample. Just click and go slightly here. This graph shows dependency of measured coefficient of spin-orbit interaction versus measured anisotropy field. Each dot corresponds to a measurement of a different nanomagnet made on the same wafer. There is a slight variation of thickness over the wafer and a variation of the quality of the interface. That is the reason why the properties of nanomagnet which fabricated on the same wafer are slightly different. You see there is a clear relation between anisotropy field and coefficient of spin-orbit interaction. A large coefficient of spin-orbit interaction corresponds to larger anisotropy field, meaning the slope of this dependency is positive. Let us check another sample. For example, Ha.05b. For this sample, the similar dependency is very clear. For this wafer, coefficient of spin-orbit interaction changes from a negative to positive value. The spin-orbit interaction is stronger when the quality of interface better. This is a better interface sample, not as good interface sample here. Remember, the strong spin-orbit interaction is originated or created at the interface due to the orbital deformation. The sharper and the smoother the interface is, the larger the orbital deformation is, and therefore the larger the spin-orbit interaction becomes. Since the anisotropic field depends on the intrinsic magnetic field and the strength of the spin-orbit interaction, the larger coefficient of spin-orbit interaction makes the larger anisotropic field. As we can see, exactly what we can see from this dependency, positive slope. This similar dependence is due to a thickness variation. The contribution to coefficient of spin-orbit interaction is negative from bulk and positive from interface. In nanomagnets, the bulk and interface contributions are averaged. For a thick nanomagnet, a negative contribution of bulk becomes larger. As a result, the average or total coefficient of spin-orbital interaction becomes smaller. A thicker nanomagnet has a smaller anisotropic field as well. You can read more thickness dependence in this file. I will talk about it in more detail a minute later. Therefore, the tendency due to the thickness variation is similar, as we can see here, meaning it has a positive slope. We can check another sample, for example, Ha.05b. The same tendency, again the slope is positive. However, this tendency does not hold in a nanomagnet containing many layers and therefore many interfaces. First, let's take a look at the sample Ha.39b. The nanomagnet consists of only 3 layers and 5 interfaces. As a result, coefficient of spin-orbit interaction is positive and rather large. The slope is still positive. However, when we look at the sample with more layers, for example, Ha.45b, it also have a very high coefficient of spin-orbit interaction, but the slope becomes negative. And if we look for samples with even more layers, like this one, and more layers, the slope is negative. A minute ago, I just explained the reason why for single-layer nanomagnets the slope is positive. Both the thickness variation and the variation of the strength of spin-orbit interaction lead to a positive slope. In a multilayer nanomagnet, there is another strong mechanism which leads to negative slope. The reason why this slope becomes negative for multilayer nanomagnet is as follows. The anisotropic field is defined by intrinsic magnetic field and the strength of spin-orbit interaction. When the interface becomes better, spin-orbit interaction becomes stronger. As a result, coefficient of spin-orbit interaction and anisotropic field increases, and we have a positive slope. However, it is only the case when the intrinsic field is independent of the interface quality. It is not always true. The demagnetization field, which contributes substantially to intrinsic magnetic field, is created and depends substantially on the interface quality. When the quality of the interface becomes better, the demagnetization field increases. As a result, the intrinsic magnetic field decreases. An anisotropic field decreases. Therefore, we have two opposite tendencies which affect anisotropic field. Spin-orbit interaction increases, which leads to increase of anisotropic field. And the demagnetization field increases, which leads to decrease of anisotropic field. For multilayer nanomagnets, the second tendency becomes dominated. Next, let us compare the data of many samples and see a wider picture for the relation between anisotropic field and coefficient of spin-orbit interaction. For this purpose, go to the Nanomagnet page, just below content. Yeah, this graph, just click on it. This graph shows the data of all nanomagnets I have measured so far. A different color of different shape corresponds to different wafer. Different dots correspond to a different nanomagnet made on the corresponding wafer. The stars indicate multilayer wafers. As we discussed, the slope is mostly positive, except the multilayer structures, for which the slope is negative. You can notice that data is rather sparse. For a nearly identical wafer, the measured data is rather different. The reason for such a large difference is the difference in the sputtering parameters, the annealing temperature, and the fabrication technology. However, the difference in structure affects the nanomagnet characteristic the most greatly. The data for multilayer nanomagnet stars is clearly far away from a single layer nanomagnets or other shapes. Once again, I would like to discuss the key factors which mostly affect the anisotropic field and coefficient of spin-orbit interaction. I will discuss the specifics about the influence of each factor. There are two key factors. The first factor is the quality of interface. The second factor is the nanomagnet thickness. By the quality of interface, I mean three qualities: roughness of interface, contaminations at the interface, and sharpness of the interface. As I have explained to you before, for the studied nanomagnets, the spin-orbit interaction and consequently magnetic anisotropy are created at the interface due to a deformation of atomic orbitals at top layer at the interface. For rough interface, those deformations are in slight different directions. As a result, the spin-orbit interaction becomes smaller. Additionally, the roughness influences the demagnetization field. The contamination means that there is an atom of another type at the interface. Such an atom breaks the periodicity at the interface and therefore the degree of deformation. As a result, the spin-orbit interaction decreases. Next, the sharpness. When the interface is not sharp and the change from one material to another material is smeared, the orbital is more like bulk type without or only with weak deformation. As a result, the spin-orbit interaction decreases. All the roughness, the contamination, and the sharpness of interface influence both the strength of spin-orbit interaction and the magnetization field. Next factor is the nanomagnet thickness. The influence of thickness is more obvious. The thicker nanomagnet is, the more the bulk properties influence the property of the whole nanomagnet, and the smaller influence of the interface. In the case of a thinner nanomagnet, the influences are opposite. I would like to discuss the thickness dependencies in more detail. Both the anisotropic field and coefficient of spin-orbit interaction depend on the thickness. Usually, the interface contribution to coefficient of spin-orbit interaction is positive, and the bulk contribution is negative. As a result, the thicker nanomagnet is, the smaller coefficient of spin-orbit interactions becomes. At least it is a tendency for amorphous and isotropic materials like iron-cobalt or iron-cobalt boron. The anisotropic field decreases with thickness. This fact is rather easy to calculate. There are few steps and few formulas. One is to take the total magnetic energy and minimize it. The mass is described here in great detail. These graphs show the calculated magnetic energy as a function of the film thickness. The anisotropic field is following the same dependence because the magnetic energy is just a product of the anisotropic field and the magnetization. The equilibrium magnetization of thick nanomagnet is in plane, because in this case the bulk contribution dominates, and the influence of the demagnetization field is stronger than the spin-orbit interaction. The equilibrium magnetization of a thinner nanomagnet is perpendicular to plane, because in this case the interface contribution dominates and the spin-orbit interaction dominates over the demagnetization effect. The thickness at which the direction of equilibrium magnetization changes from in plane to perpendicular to plane direction is called the critical thickness. You can calculate the critical thickness from here. Just go to page 3. This is formula to calculate dependence of coefficient of spin-orbit interaction on thickness, and this is formula to calculate critical thickness. The formulas are simple. Experimental data are more complex though. The fact is the magnetic properties of nanomagnet depend equally substantially on each parameter, the thickness and the interface quality. The interface quality often depends on the thickness, so it's not as simple. I will talk about it in more details in the following parts of this video set. If you are interested to see the content and other parts of this video, you can find the links below this video.